Hello, everyone. Welcome to week 4 of our online learning. This week, we're going to be talking about the Hertzsprung-Russell diagram, also known as the HR diagram. And the purpose of the HR diagram is to classify stars. Okay, it's a graph where we put our stars so we can understand more about them. So the first activity you're going to have online is a fun little celebrity HR diagram. And this is just getting you used to reading and thinking about the X and Y axis and where we would put stars. Celebrities are also called stars. Ha ha. All right, so you're going to put them on here, and a lot of this is based on your opinion. So across the x-axis, we have hotness. How hot and cute do we think they are? If they're really hot and cute, they're going to be put over here. As we move this way, they're kind of cute and hot. Over here, they're average, and down here, I don't think they're very hot at all. Not good looking. Star power is on the y-axis. If I keep them down here at the low section of star power, I'm saying they don't have very much power. I don't really know who they are. Nobody knows who they are. They don't have very much power. As we move upward, okay, these stars would have average star power. And as we go further up, they would have more power. I would think a celebrity that we really know, everybody knows who they are, and they're on commercials and advertisements. They're there because they have a lot of power and we think they can influence people. So this is what we're going to do. I'm going to do these two lovely little fellas over here as an example for you. Now, if you had trouble last week moving your items from here and putting them over here, you need to check up in your right corner and make sure it does not say presentation. If yours says presentation, it's going to look a little different than my screen. Then you might have trouble moving these. Click on this and change it to edit mode. If it's in edit, you will be able to grab these and move them as well as much as you want. Okay. All right. So I'm going to start with SpongeBob. And I'm going to bring him over here. Now, this would be average, but I don't really think SpongeBob is average. In my opinion, he's not very cute. He's not the ugliest I've seen, but I don't think he's very hot. So I'm going to move him down here. But I think he has a lot of star power. I think grandmas know him, and middle-aged people and teenagers and young people. I think everybody knows who SpongeBob is. So I am going to put him over here, and I have just lost him. Welcome to technology. All right, there he is. Let's try that again, SpongeBob. Oh, look, it even glitches for Miss Wiki, and I know what I'm doing. Sorry, guys, who can't help computers. So again, not so hot, less than average, but a lot of star power. Casper, on the other hand, I think is absolutely adorable. So I'm going to move Casper and put him in cuteness. I don't think he has as much power as SpongeBob. I don't think as many people know who he is. So I'm moving him down here to pretty darn cute, maybe not the cutest, and I'm going to give him some average star power. People know him, but not everybody does. This is my opinion, and I'm going to graph him this way. You can graph people as you want. Every once in a while, you're going to come across some that are pretty darn close. I might think he's fairly average. I might think SpongeBob is also fairly average. Okay, their hotness might be the same, but I still think people maybe just know SpongeBob a little bit more than him. I could put him here. It's okay if they overlap. Sometimes they are. But when I go back and read this, I can tell. Hotter, well, they're both the same hotness. They're on the same line, so looks, they're the same. But as far as star power, when I come over here, here is average star power. Here's a little bit more as we go up. So I know he has more star power than Casper. So that is how you read this HR diagram, and that's what you will be doing with it. The next two slides that you have to look at this week are just talking about apparent brightness versus absolute brightness. When we look out at the night sky, we can see faded stars, dim stars, bright stars, and we might think, boy, that bright star must be really hot. But you know what? In actuality, that really dim star might be much hotter and even much bigger. It's just farther away. Distance matters. So down here, this representation shows us apparent brightness is what it looks like to us, what it appears like. This one appears brighter because it is closer. This one is further away, and you know that a fire is going to be much brighter than a candle, okay? The flames are, but it's so much farther away that we're not going to see the brightness the same. So to us, it would appear less bright, but that is not the truth. So apparent brightness is how does it look for us on Earth? Absolute means the truth. It's the absolute truth, okay? This one appears brighter and this one appears dimmer. And if you notice, these are the same distance, okay? So we do have to consider distance to determine which one is actually brighter and dimmer, as long as they are equal. Absolute means the truth. So you can look at those diagrams again to help you remember that. Not something you need to memorize, just something to help you understand how we classify stars. You will watch this video. Please do watch it. It's very short, but it also explains how to read the HR diagram again. He goes into more information than I will. And then after that, you will be doing an activity where you put these objects where they go, okay? And some of these shapes might have 2 words in them, but it is really important to know if it's over here, these numbers are different than these numbers for temperature. So you're going to have to think about it. Which word goes here and which one goes here? Placement does matter. All right. All right. So let's talk about that then. Let's look at our HR diagram. And I'm going to hit presentation mode for you so that it's a little bit bigger. Sorry, it takes a moment for everything to boot up here. All right. What do we need to know about the HR diagram? This is the true HR diagram. There are many different ones. They look different. This is a very simplistic, basic one. It helps us understand what we need to know. On the x-axis is going to be temperature. We measure temperature of stars in Kelvin. Stars are too hot to measure in Fahrenheit or Celsius. So the next unit of measure after Fahrenheit and Celsius is Kelvin. This is extremely hot. No matter whether you're the hottest star or the least hot star, you would be able to burn up a planet or a person very quickly. So please remember that when we talk about cool stars or cooler stars, we are not talking about the temperature as being cold or cool. It's just cooler compared to another star. What's weird about this, and you really need to pay attention to the numbers, is that we start out with the hottest on the left. I'm pretty sure in math class and other things that we've studied in science, we usually start from small and get bigger as we move outward. That is not the case for the HR diagram. So around 40,000 degrees Kelvin is the hottest stars. And as we move this way, we are decreasing the amount of heat that a star gives. So down here, our cooler stars are 2,500 degrees Kelvin. Remember that 2,500 degrees in an oven would be ridiculously hot, okay? But Kelvin, boy, that is super hot. So even our coolest stars, oh, look, they happen to be red. That's weird. The red stars are our coolest stars. Some are small, some are really big. So size doesn't matter for temperature, okay? The temperature, size is not going to tell us an object's temperature. Color will. So the red stars are the coolest. Orange stars would be the next coolest. We're getting a little warmer. Our sun is an average temperature star. As we move this way, we get into the white stars. We're getting pretty hot here. 10,000, right? 15,000, 20,000 degrees Kelvin. We're going to have our white dwarfs, super hot stars, and are going to have our blue giants. So dwarfs and giants, yes. Size, in this case of temperature, does not matter. And as we keep moving towards the hottest, we're going to see blue. And if you've ever looked at a flame very carefully at the bottom of a match or the bottom of your gas flame, you will notice that it's white and blue down there. And then up higher, it's yellow, orange, and red. So if you look very carefully at that, you will see that this is true. Now, I know the hot orange red part of a flame is going to burn me. It's going to burn my skin. So I'm not going to put my finger there. But the blue and white heat is much hotter. So this is true for objects that have heat on Earth as well. So please pay attention. Temperature along the x-axis, you're going from the hottest to the coolest this way. Just look at the numbers, boys and girls. You don't have to memorize. Just read your chart carefully. On the y-axis, we're going to have luminosity. And luminosity is just a fancy name for light, brightness, okay? Another word they use is magnitude. Magnitude means how bright a star is. So you might see the word luminosity. You might see the word brightness. You might see the word magnitude. You just have to remember that we're talking about the brightness of the star on the y-axis. So I'm going to start here, not down here at the bottom corner. This is 1. We are comparing everything to our sun. Okay, we always compare to what we know. So this means 1 times the brightness of our sun, and 1 times anything, boys and girls, equals itself. So all these stars right here along this line are the same brightness as our sun, okay? And our sun would be right over in here. All right, because it's a yellow star. So we would find it here. I'm going to say this one is probably our sun on this diagram. So 1 is ours. So anything below this 1 means, and these are negative numbers, anything below it means it's less bright than our sun. All of these are going to be less bright. Anything above this, okay, 10 to the second power, 10 to the fourth, we're just adding more zeros behind it, right? So this is 10 with extra zeros, right? 2 zeros. Remember our scientific measurements, right? Do we know how to read this? I hope you do. All right. Anyhow, so we have, this is going to be much brighter than our sun, even more brighter than our sun. And then these are our brightest stars up here at the top. And if you notice, these happen to be giants and supergiants. And red supergiants are brighter than red giants. Okay. They might be the same temperature, but if you're bigger and the same temperature, you are going to be brighter because more surface area is showing. Here, I can only just see a little bit around that outside edge. Here, I see a lot. The more you can see, the brighter it's going to be. That kind of makes sense. So up here at the top are our brightest stars. Down here at the bottom are our least bright, and right here is the same as our sun. So you're going to need to be able to read this HR graph. All right, I also see some patterns here. I see a line right here. Do you see this diagonal line? It waves a little bit. We have every type of star along this line, okay? I shouldn't say every type. We don't have our big giants over here. Some of these are giants, okay? But these tend to be bigger stars right here. These tend to be smaller stars. These are really small dwarf stars. They're really, really small. They're hard for us to see because their temperature is low. Their brightness level is low. And if they're really far away, it's kind of hard to find these because they're not very bright, they're not very hot, and they're small. So it's going to be hard for us to discover those. Whereas if you're really big, we're going to be able to see you a little better, especially from far away. So along here, I have blues, I have whites, I have yellows, I have reds, I have all the temperatures. This is called our main sequence. Okay, this is the main sequence. Most stars, not all, but most stars, when they are born and they would fall on this main sequence here somewhere. Okay. And if you remember, our star is just a very young 4.6 billion years old. It's not very old. It's got another 5 billion years to go here. Okay. So they're going to spend a long time here. This is toddlerhood, little toddlers. This is elementary students and middle school students and high school students and young adults like Miss Painter and Mrs. Lavelle. They're, our young people are going to fall along this line here. All right. If we compare them to people, and they are going to spend quite a long time here. All right, they will be here for quite a while. And then let's talk about our sun. What happens after another 5 billion years? Well, we know it's going to use up its hydrogen. It's going to make more helium. Helium expands, it gets bigger. And so our star is going to become a red giant. It's going to move over here. It'll move off the main sequence. So these stars at once upon a time were probably over here. Not all of them, but most of them were here. And now they have moved off the main sequence and they are going to spend their later adulthood up here. And, again, we're going to talk for our sun another 10 billion years. It's going to be a really long time. This would be, where I would be in my stage of life if we were talking about a person up here in the red giants. So if I look up here, when we come off, we're bigger. Why? Because they've used up a lot of their energy from here. And they have expanded because they've made helium. So they've grown in size. All right. But their temperatures probably have decreased a little bit. I know our sun has. It's decreased. It hasn't yet. I'm sorry. But it will. It will decrease, but it'll be bigger. So it'll be brighter, but its temperature will be less. Okay. When I read this. Then what happens? We stay here for quite a long time. We use up more energy. We blow off our outer shell and we're left with our hot little core, and we would drop down to here below the main sequence. Our star will become a red giant and then it will become a white dwarf. White dwarfs are hotter than the original sun, than the red giant. It's hotter because it's the very inner hot core. Think about our planet. Remember, we talked about that. The surface touches space, it's going to cool off faster. That inner hot core is going to stay super hot for a really long time. So we're left with our inner core. It is less bright than our sun because it is smaller, but it is super hot. All right. So down here is going to be the end of life for stars. And we keep it pretty simple in 8th grade. You can find HR diagrams that have all kinds of other stars put on here. But this is the basics of it and what you need to understand. And it just comes down to reading this. So as you go through the rest of the activities, make sure you read on the side. It reminds you of what's going on. Look back to it when you're doing the activities that we have put in there for you. If you have any questions, please feel free to contact Ms. Painter or myself. We'll be happy to answer them. And please watch the video that's at the beginning of this lesson. I think you will be able to do a great job on the HR diagram. Thank you, boys and girls, and have a great week.